colleagues, welcome to attend the annual lecture by Professor Rosalie Iemhoff at Wuhan University on logic and the foundation of mathematics. Firstly, it's our great pleasure to introduce the speaker. Professor Rosalie Iemhoff got her PhD in mathematics and theoretical computer science from University of Amsterdam in 2001. Currently, she is a full professor of formal reasoning in the Department of Philosophy from Utrecht University. He works on a lot of fields. His research areas include foundations of mathematics, truth theory, mathematical logic, philosophical logic, intuitionistic logic, non-classical logic, probability logic, model logic, and proof complexity. She is a well-known international expert in logic, and he has done a lot of editorial works in some important journals. She is the editor-in-chief of the Journal of Philosophical Logic, member of editorial board of the book series Perspectives in Logic, former editor of the Review of Symbolic Logic, member of the board of the Hinton Foundation, former editor of Mathematical Logic Quarterly, editor of Stanford Encyclopedia of Philosophy. Okay, we also give a brief introduction of the interlocutor, Associate Professor Lin Zhe from XiaMen University. He got his PhD in mathematics and computer science from, I'm sorry, I'm not sure my pronunciation of this university. It's a university in Poland. He got his PhD from 2015. His research areas include proof theory, logic and computation, algebraic logic, and non-classical logic. Okay, that is a brief introduction. Now let's give time for Professor Rosalie Iemhoff. She will give an online lecture at Wuhan University. The title is On the Non-Existence of Proof Systems in Universal Proof Theory. Please and welcome.
Okay, I start sharing the screen.
Yeah.
I think here it is.
Yes.
Okay. Thanks. Introduction. Very nice to be here. I have not been to your university, or I'm not sure even that you are at the same university in the audience. But I hope to visit China again sometime. I was a couple of years ago in Guangzhou, if I pronounce it correctly, university, and it was a great experience. So I've been asked to give a lecture, well, on a topic in logic, and I will talk today in these 2 hours or 1 hour and 45 minutes about proof theory. And in fact, I realize now that the title of my talk is in fact the title of the last chapter. So the talk will consist of 3 chapters. One is about is an introduction to pure proof theory. And the second chapter is then, well, continues this, but then also provides some broader perspective. And in the last chapter, that is in fact the chapter to which the title refers. Then I will really talk about the existence and non-existence of proof systems and how you could prove results of that form. And all that is part of a project that we call Universal Proof Theory, and that has developed over the last 5 years that I work on very, very often. Is my main topic of study at the moment, at least. So I have 3 chapters. Now, the thing is, when we would be in a room and I could see your faces, I could see when I talk whether I say something that you maybe already know, or in fact say something that you've never heard of. We don't have that opportunity now. I'll just do my best. But I really want to say, please feel free to ask a question. I don't know, even just start speaking or raise your hand in the Zoom. That is totally fine with me, yeah? But you may also, of course, keep your questions till the end if you prefer that. Now, proof theory is a large field, of course, in logic, and it has, well, applications in mathematics and philosophy and in computer science. I wanted to start, because this is not like a regular talk, but also meant like as a lecture to introduce you to an area. I very briefly say some things about the origins of proof theory. I want to start with that. And from that on, the talk will become more and more technical. And then in the last chapter is in fact less technical again, because then I again will give kind of a broad view with a lot of results, but no technical details, while in the middle, chapter 2 and the end of chapter 1 will be more technical, and will provide as many details as I think are useful. So the origins of proof theory. So as some of you may well know, in the year 1900, at the International Congress of Mathematicians, David Hilbert, who was by that time one of the most famous mathematicians in the world, posed 23 very famous problems, the Hilbert open problems at that time, that were open, and he thought were very important, or maybe amongst the most important open problems at that time in mathematics. And the second one was a problem that we now would say is a problem in proof theory, but that term wasn't used then. Namely, Hilbert asked for a proof of the consistency of the axioms of arithmetic. So we have piano arithmetic, which is this well-known, beautiful axiomatizations of the natural numbers with the induction axiom. And Hilbert asked for a proof of the consistency of this theory. Yeah. It is, of course, and at that time and also now, it's of course not obvious that such a theory is consistent, in the sense that it is an infinitary theory. I mean, it's supposed to talk about the natural numbers, which is an infinite set. And then, of course, one can maybe have doubts whether this really is a secure foundation, so to say, for the natural numbers. So that was the question. And also there was added, the question was to prove to via proof theoretic methods. So in the words of Hilbert, to conquer this field concerning the foundations of mathematics, concept of a specifically mathematical proof itself into an object of investigation, just as the astronomer considers the movement of his position, the physicist studies the theory of his apparatus, and the philosopher criticizes reason itself. So it's kind of a reflection for the mathematician, not only proving things, but also starting to study the thing that he's doing, namely proving. Yeah, that's behind this. And that was a really genuine, view, so to say, on proofs. So, and from this, is, so to say, that you could say is the start of Hilbert's program, and that you study proofs and that you build proof systems for parts of mathematics as a kind of rigorous axiomatization of mathematics. So you have a piece of mathematics like the natural numbers, and now you want to really axiomatize it and formalize it and be very precise about what you assume and what you then infer and things like that. We're going to see full proof systems and details in a moment. This is just a general idea. And then proving consistency, as Hilbert proposed, is by showing that you have this formal system now, this representation, and then that you show that that representation cannot derive inconsistencies. Yeah, that was, so to say, the idea. Now, oh, sorry, wait a moment. Yeah. Now, also very well known is, of course, that Kurt Gödel in 1931, so 30 years later, proved that no sufficiently strong theory can prove its own consistency. And that's the Gödel's second incompleteness theorem. And that is in general considered to be the end of Hilbert's program. Because if a theory like, for example, piano arithmetic, which is already quite strong, is sufficiently strong, if PA cannot prove its own consistency, how could an even smaller or finitary system prove that as well? So although you can have a lot of questions about what do we mean with proving consistency, so there are certainly still people arguing that maybe this is not the end to Hilbert's program, but that's not so much of my concern here. I just wanted to show kind of the beginning, what happened in proof theory. Yeah, and also I myself consider that Hilbert's program in this strong sense is not possible. But the beautiful thing is that sometimes from a wrong idea, bright as Hilbert was, we still could say, well, this Hilbert program, that was not the right idea in the end, of course. But it's the beautiful example of that from a wrong idea, something very positive can emerge, namely proof theory, because all the other intentions of Hilbert, namely to make, to axiomatize parts of mathematics, to rigorize them, to formalize them, all these things, to make, so to say, the proofs in this area more precise, that all remained, and that all became proof theory, and that's an area that is still very much active and alive today. So that's like, in a nutshell, you could say, the origin of proof theory. Now, having said that, now let's take a next step and look a bit further into proof systems. Okay, what are they? What kind of variations are there? And then one could say that in the early days of proof theory, so the beginning of the previous century, proof systems were mostly Hilbert systems, later called Hilbert systems. This was not a name from that time. And what do we mean by that? It's often also when you are a student in logic, these are the first systems that you are taught. And here's an example for classical propositional logic. So this is what we call a Hilbert proof system. And to keep it simple, I restrict myself here to the language with negation and implication so that I don't have so many axioms to display. And then there's, for example, this proof system, let's call it H1, which consists of 3 axioms and a rule. And when I take a sip of my tea, you can look at the axioms. So these axioms are clearly true. The first one is a kind of weakening axiom. If you have a formula phi, then of course any other formula implies that formula. The second one is a kind of opposite of contraposition. You have the third one that I'm not going to read aloud, but I hope you see that that is clearly valid in classical propositional logic as well. And we have, of course, the well-known rule of modus ponens. And now you can prove things, of course, in this proof system, H1. For example, when you have 2 axioms, on the left the weakening one and on the right the long one, and you see that I have on the right the axiom, this is an important aspect of proof systems, is that you write the axioms where what you in fact mean is all instances of the axioms. Yeah. So what you see is that with the axiom at the right, the long one, I have instantiated in a way that the chi, which is in the axiom, is instantiated by phi. Yeah. It's of course allowed, I can do it. And then when I apply modus ponens, I obtain a well-known valid formula, namely that phi implies psi, implies phi, of course, because phi implies phi always holds. Yeah. Okay, so far so good. But there are many things that you can see that you could maybe criticize once you are starting to get interested in how precisely proofs look, what they look like, how large they are, etc. And one of the things is the observation that proving phi implies phi in this system is no easy thing. And in fact, I always torture my students in the first class on proof theory by asking them to prove this, phi implies phi. I'm not, of course, going to ask you now, but that ain't that easy. And of course, that feels strange because this is more or less the first tautology that you think of when you think of tautology. So, okay, maybe not that natural. That's one criticism. Second, the axiomatization seems kind of arbitrary. You have also others. And here at the bottom of the slide, I have a very ugly one, namely still with the rule modus ponens, with only one axiom. And I hope you excuse me that again, I'm not going to read that whole axiom. I just want to make the point that, of course, this is an axiomatization, but it teaches you nothing about classical propositional logic, seems arbitrary, probably proofs will be very unnatural because a thing as phi implies phi, you now have to deduce from this ugly axiom. Now, that is not really what we want. Yeah, so I'm now bashing Hilbert systems a bit. Of course, there are very, how do you say, useful applications. And for example, in a field like complexity theory, a complete proof complexity theory, they play an important role and they're exactly right there. But for the line of research that I'm going to talk about in proof theory, I may bash them a little bit because they are not useful for us here. Yeah, that's the perspective you have to have. Now, then in the 1930s, Gerhard Gensen developed proof systems for the first time that you could say are natural or way more natural than the systems that were there before. And in his own words, so this system was called natural deduction, so the word natural, of course, in there. And Gensen says that to set up a formalism that reflects as accurately as possible the actual logical reasoning involved in mathematical proofs. That was his aim. And that's a very different aim from the Hilbert systems. It's just axiomatize it in any way you want. But Gensen wants something more. He wants to axiomate that, yeah, classical propositional logic, but also other theories, we'll see. But the extra thing is he wants to do it in a natural way. Yeah. Now, of course, it's for yourself to judge whether you think that's natural, but let's at least have a look at it. So improving natural deduction, ND, starts from assumptions and derives further statements by natural rules. So this is already something that you may recognize from your own mathematical proofs. And you assume things and you derive further things. So far, so good. Now, I'm not going to give the full system because, in fact, I want to end up with sequent calculi, which are closely related but a bit different. And these I will give in full detail. So I'm going to give examples for some connectives. Yeah. So an example of two rules in Gensen's natural deduction system are here on the slide. On the left, you have the introduction of conjunction. Well, you obviously see why it is called that. And on the second one in the middle is the elimination of conjunction, also clear why it is called that. And on the right side, you have ex falso quod libet, and that's the rule that says from falsum you may conclude everything. So these are two typical rules. And give me a moment. No, I think I didn't say it, so let me say it here. So you have to think of proofs that probably you understood that already. They are, in my case, let's say trees. So you have your assumptions and then you apply rules. And the rules can then be of the form that I just have here in the example. Yeah. But of course, there are more in Gensen. In the case, they are for every connective and the quantifiers you have rules. Yeah. But I leave them implicit. And what is very different from the Hilbert systems here already is that in some sense you have the feeling that the meaning of the connectives, such as conjunction, is really described or captured by these rules. So as Gensen says, the introductions represent, as it were, the definitions of the symbols concerned, so the definition of conjunction here, and the eliminations are no more in the final analysis than the consequences of these definitions. Yeah? So meaning that together the elimination and the introduction will really define what conjunction is. And in this way, Gensen views these rules as natural. Yeah, that's the idea. I hope many of you have seen this in a logic class at some point. Now, I want to say, before we go to the sequent calculi, I want to say something about natural deduction that is difficult. And I also want to say, because historically, this is how it led to the sequent calculus. So let me briefly say something here. So if you look at the proofs in natural deduction, so the system seems quite natural, very beautiful, but in how close it is to mathematical reasoning. But there's something with the form of the proofs that we have to discuss. So a proof is called in normal form in natural deduction if it doesn't contain detours. And rather than defining this officially, I just want to give you an example of a detour on the slide here. That is that you take some superfluous steps in your proof. So as you see here, from phi1 and phi2, you conclude phi1 and phi2. And then you conclude phi1. But then, of course, you started with the phi1 on the left side. So why then do this step in between? That's just superfluous. It makes your proof longer and it's not unnecessary. The complete definition of normal form is larger, of course, a bit more involved, but this is the idea. Yeah, don't take unnecessary steps. Yeah. Now, these normal proofs are nice for many reasons. I'm not really going to mention which reasons that are, because when we go to the sequent calculus, we'll see similar proofs in the kind of normal form that have good properties. And at that point, I really will explain more about, will tell you more about why that is so useful. For the moment, let's continue with the story. So proved normalization for intuitionistic natural deduction, but wasn't able to prove it for, or at least not directly for classical logic. And that is why Gensen moved to the sequent calculus. Later, Prawitz and Jan van Plato and Sarders proved, in fact, classical logic has normalization also in a direct way, but Gensen did not. So Gensen took another step, namely to prove this normalization in natural deduction. He developed a proof system called the sequent calculus that's very closely related, for which he proved kind of a normal form. It has a different name there, but different. And in this way, and translating it, he could then prove normalization for natural deduction. Not going to take this step. I just wanted to arrive at the sequent calculus. Yeah, these will be our proof systems for today. And it's also the case that although Gensen in some sense developed sequent calculus as a tool, they are so beautiful and so useful that today there are primary proof systems, especially in structural proof theory and in universal proof theory, what we'll talk about today. This is really the proof system that people use in this area most. So they have, they started as an auxiliary proof system, but now they are in many areas, in fact, the main proof system. And I hope to convey to you why that is the case, or yeah. So what is with the sequent calculus, there's one big difference with the natural deduction is that it's no longer about formulas, but are expressions that are called sequents. And before I define them, I just wanted to tell you that it's in fact kind of natural deduction where you put the assumptions not at the top of the proof, but at the left of the sequent. So I hope this slide is a little bit instructive. In natural deduction, you would have that from assumptions gamma, you conclude phi. Now, if you put the assumptions on the left, then in natural deduction, you would say from assumptions gamma, I can derive phi. We're now at the second part. Then we go to the third part because we generalize it a bit. So we don't only derive from gamma formulas, but sets or multisets of formulas. That's a generalization. And then we replace the derivability by what we call the sequent arrow, and then we have what is called a sequent. And now I'm going to define it officially, yeah? But this is kind of the idea how you have to think about it. Okay. Definition, sequent calculi. So for the moment, I'm going to talk about classical logic because that's so nice and simple and I can give you all the details, but in fact, we are interested in the end in way more logics, conditional logics, modal logics, intermediate logics, etc. Yeah, but this is for simplicity of introducing sequent calculus. So we have a language of propositional variables, we have constant falsum, we have the usual connectives, and negation I always like to define as phi implies falsum. Oh, don't know what happened here. Ah, okay, something went wrong with the picturing. At the background here, you see that's Gerhard Gensen, but I'm sorry, now on the slide it's a bit ugly. With IPC, I define intuitionistic propositional logic, and intermediate logics are all the logics between IPC and CPC inclusive. I decided, because I cannot, so to say, define everything, that would take too much time, so I hope I can assume that you know what intuitionistic propositional logic is, and if not, think of a weaker logic than CPC. Yeah? One important thing of notation here, when we have a set of connectives, the C fragment of CPC, of classical propositional logic, are all the valid formulas that contain only connectives in the fragment. We use that sometimes. Yeah. Now we go to the definition of sequent. So the sequent is an expression of the form gamma sequent arrow or arrow delta, and gamma and delta are multisets. Sometimes people use sets, sometimes people use sequences. Not so important here, we use multisets. Yeah, it's also what is mostly done. Notational point, I omit the brackets, which is also usual. So you see on the slide how I, in gray, how I omit the brackets in the notation. That reads better. Now, as I'm officially defining them, I should also say what the interpretation is. So the interpretation of a sequent is just a formula. And it is a formula that you take the conjunctions of gamma, and that implies the disjunction of delta. So that's the interpretation of the formula. So the arrow is read as an implication, gamma is read as a conjunction, and delta as a disjunction. That's something you have to remember. It's important. So two innocent examples. The first one, you have phi and psi on the left, and phi and chi on the right. And then you interpret that left the conjunction, phi and psi, and right the disjunction. And I wrote this explicitly because they are multisets. So formulas like chi may occur more than once. And in the interpretation, we also really take all of them. Of course, it's equivalent to the version where you leave out one chi, but officially the interpretation is really that formula. I leave the other example for yourself to see. Now, so these are the expressions, no longer formulas, but sequence. But of course, sequence are interpreted as formulas. So implicitly, it is about formulas. Now, a sequent calculus is a set of rules. And a rule is just what you think it would be, but then with sequence. So you have premises S1 to Sn sequence, and you have a conclusion S0, which is also a sequence. These are rules, yeah? And the calculus is just a set of such rules. And an axiom has no premises. Yes, I let you look at this, then I can take some tea. Here you see why I use a fragment, because there are already many rules to show. So of course, the disjunction fragment of CPC is totally trivial, but just for now to make you acquainted with the system. So usually you have the axioms P, arrow P, clearly valid, of course, and bottom arrow empty. And the disjunction of empty is also bottom, so it's valid. Now you have rules for the logical operators. I'm not going to discuss all of them, but look at the right rule for disjunction. So what you see is very beautiful in the sequent calculus. You introduce connectives to the left and to the right, yeah? And there's that symmetry. And if you look to the right disjunction rule, to see that that is valid is just to see that if the interpretation of the premise is valid, then so is the interpretation of the conclusion. And of course, we know that because the comma on the right is interpreted as disjunction. So of course, this is a valid formula. Yeah. The other one I leave to you. I want to have a look at the structural rules. Structural meaning they are not about the connectives, but they are things that are obviously true and that we need. So for example, at the left, you see the left weakening, the W's for weakening, left weakening rule. And then you see that what you can do if gamma arrow delta is valid, the interpretation of that formula, then the interpretation of gamma phi arrow delta is also valid. Why? Because at the left, the phi is a conjunction that you add. So it's gamma and phi implies the disjunction of delta. And that's certainly valid when the premise is valid. And the same is for the other rules. So you have also right weakening and contraction. Sorry, give one. Contraction is that you have to form the same, you have copies of the same formula and you may reduce the number of copies. These structural rules may seem a bit strange when you see it for the first time, but they are actually extremely important. So we'll hear more about it. Now, a proof, to be precise, I wrote it down on the slide. Let me also say it in words here. A proof is just what you think. It's a tree, and the leaves are axioms, instances of axioms, yeah? And the rest of the tree is made by applying the rules to the sequence. Yeah, so if you have some sequence that are the premises of the rule, then you add the conclusion of the rule and you have again a proof. And that's what's written here in the definition. So these are proofs in the sequence calculus. And here below is a very innocent proof that P implies P or Q. Yeah, so you see you have your P implies P, you weaken with the Q, now you here see how the weakening functions, yeah? And then you conclude P implies P or Q, yeah? Simple. I have another one, but I think in view of the time, I continue here, because otherwise I don't have enough time. Now, of course, I thought I have to show you one time the whole sequence calculus for classical propositional logic. Normally, I often don't do that in talks because there are so many rules, but if it should be kind of also introductory, I think we should look at it. So here is the whole slide. Let me tell you, the axioms and the structural rules are just as on the previous slide. We saw them already. Then we see the line with the rules for disjunction. We also saw them already. And then you have two lines for the conjunction, left and right introduction, and for the implication. And maybe for us together, let's look at the right implication. Then that is valid, because here you see classical logic at play, really classical logic, not intuitionistic. Because if the premise is valid, it says that gamma and phi, I'm now saying gamma instead of conjunction gamma, yeah? Gamma and phi implies psi or delta, yeah? And in classical logic, then you indeed have that gamma implies phi implies psi or delta. Why? Because either phi is valid, and then you have the premise, so you have psi or delta, or phi is not valid, and then of course phi implies psi is valid. Yeah, so that's in fact not a totally trivial reasoning, and also it's really classical reasoning. Yeah. Now, you don't have time for it now, but believe me, all these other rules are also valid. But I hope you see the elegance of the system and the symmetry. And I want to show you one proof because it's an interesting one for later. So a proof of the law of excluded middle. Yeah. So what we have, how should we do that? Again, weakening is necessary here. So we start with P implies P. We weaken with bottom. And then remember that not P is P implies bottom. So the next step is an application of the rule that I just discussed, namely P implies that you can obtain the implication P implies bottom at the right, which we write as not P. And then we do a simple disjunction introduction and we have the law of excluded middle. Yeah. Okay. So this system is sound and complete for classical propositional logic. And what I mean with that is what I write here on the slide at the bottom is that the sequent arrow phi is derivable in the system if and only if phi is valid in the logic. Yeah, it's not hard to prove all that. Absolutely not. The magic is in coming up with such a beautiful system, but then showing that it is indeed complete is not difficult. What I want to say here, because we're going now in the direction of structural rules and to even better systems. So what's not so nice is this system is if you want to do proof search. And with proof search, we really mean that you start with a sequence and that you want to look whether there's a proof for that sequence. And you're going to do that by applying in reverse order from bottom to top possible rules. Now you see, and that's in fact beautiful in the system, that in many of these rules for the logical operators, the premise is smaller than the conclusion. So that might give you already the idea that proofs would terminate because you go to a smaller and smaller sequence, and that is nice because at some point you could say, well, I have found a proof or not, say it a bit hand waving. Not with the structural rules, because if you look at, for example, the right conjunction or in the middle here, the RC is called the rule, then you see that you have, suppose your sequence is gamma arrow phi delta, it might be that you have to multiply the phi, yeah? But maybe we have to multiply it again. And where will that ever end? How do we know? So for proof search, nice as this looks, is not convenient, in fact. So we're not there yet with the system that we really want. I wanted to say for IPC, the proof system, but I decide now at this moment that I'm not going to do that. I have a bit more time than I thought. No, okay, yeah, no, sorry. Well, I'm adding this. What I wanted to say is, thus, for those of you who know intuitionistic logic, I wanted to say what a standard proof system is because it's so simple to say. I don't have to show you all the rules again. The thing is, it is the system that we just saw, but the only restriction is you have only one formula at the right. And then you have, in fact, two rules, left implication rule and the right disjunction rule, that you have to reformulate a little bit, as I do here. Because on the previous slide, you really needed a premise with more than one formula on the right, and we don't have it now. But it's not hard to see that these two rules are valid in intuitionistic logic. Yeah, and you take all the rules of the previous system, and then with one formula at the right. And then, as I wrote on the slide, it's a beautiful theorem that indeed that system is sound and complete for intuitionistic logic. So I wanted to mention it to show you already that for these two basic logics, IPC and CPC, we have very nice systems, although we even get to nicer ones. And I also wanted to show you here in the example that indeed, if you allow more than one formula on the right, then the rules are not valid for IPC, because remember that I just showed you the derivation that's on the slide here as well, namely a derivation of P or not P. But as we know, the law of excluded middle doesn't hold in IPC. So this proof we should not be able to do in the sequent calculus for IPC, the G1IP sequent calculus. And of course we cannot. Why? Look at the second step. There are two formulas at the right, and that's not allowed. Yeah. one could fill a whole course with this very interesting and beautiful this fact about intuitionistic logic. But let's move on to the second chapter. I showed you sequent calculi for IPC and CPC, and two things that I want to do in this is a shorter chapter. Two things that I want to do is I want to briefly just give you some of the rules of sequent calculi for more classes of logic, so that you get an idea of how widely you can apply these sequent calculi. And then the second part of the chapter, I'm going to the real systems that I am interested in. And for those of you who know this already, this will be the cut-free and analytic systems. Yeah. And then the third chapter, as I said, will be about this project of the last 5 years in universal proof theory. Okay. So with the chapter now, the logics and their sequent calculi, I decided to not go very deeply into it. I just wanted to show you some examples, so to say. That was, And I chose, among all the logics, classes of logics, I chose modal logic, classical modal logic here as a starting point, as an example of a class of logics where sequent calculi are also very much used. So the thing is now that we have the language of propositional logic, and we add, for simplicity now, one modal operator box, but there are also sequent calculi for more modal operators, etc. It's just for simplicity. And just to remind you, so these modal logics occur, of course, in many areas in philosophy, where, for example, you want to model things about agents, what is knowledge or what is necessary. Computer science, where you often use it to prove things about runs of programs, whether they stop or not, or any mathematics, in provability logic, to name something. And of course, they are so beloved because they are more expressive than propositional logics, but still have good computational properties. So that's what we want for the proof systems, the sequent calculus as well, good computational properties. As I said, I decided to just give you some examples so that you know a little bit about what kind of sequent calculi you have to think of when we talk about these logics. So first, the logics, just some very well-known ones. We have the K logic, modal logic K, which is modus ponens formalized, so to say, plus the necessitation rule that you see here. Phi implies, or from phi you can conclude box phi. We have for the transitivity action, box phi implies box phi. I chose the T action reflexivity, box phi implies phi, and D is the consistency, not bottom phi. Consistency in case you interpret the bottom as provability. Yeah, just some examples. And what I said is already in words, how the modal. Why, as I said, I only do this because I want to show how simple it is to obtain nice sequent calculi for these logics. Because if you look at K, the modal logic, and I wrote it down there again with its axiomatization, then the G1 sequent calculus, in this case called G1K for the logic K, is just the calculus G1 CP, which we saw for classical propositional logic, with one rule, which is called the K rule. And the K rule says, in fact, that you may box, so to say, the premise and the conclusion, provided you have now one formula in the conclusion, and not a multiset here. I'm not going to explain why this is indeed a sound and complete system. Also here, it's not so difficult to show, and maybe you see the soundness easily, but if not, just believe me. Then you see that for K4, you have K, but you add the transitivity action, you see that the calculus G1K4, the middle line, is very similar because it also is the calculus for CPC, and you have the for rule. You just add the box gamma to the premise, and then you have a calculus for that logic. So also very natural, very simple. And the last one, K with the consistency, have you G1KD, and now you see that you have the calculus for K, G1K, and you add one rule to obtain these not bottom falsum, that it will also be derivable in the system. And if you think at the emptiness at the right side of that sequence, if you think of that as bottom, then you may clearly see how you can derive that not bottom falsum in that system. Okay, so very nice. Maybe let me check for myself. Yeah, so maybe let's forget the proof on the left. It is not so interesting, but the proof on the right, as I said, maybe let's just do it just because it's instructive. So you have your, I wrote here that G1KD indeed derives this arrow not box bottom. And I reminded you that negation implies falsum, and then follows the proof that you start with the action bottom arrow empty. Then you apply the D rule, so you get box bottom arrow empty. Then you weaken with empty on the right, and then you do implication to the right, and you write the negation instead of the implication. So this is how it works. So you have your systems here, and you have your sequent calculi. And as I said, this can be done for conditional logics, intuitionistic modal logics, you name it, various predicate logic. So it's very, they occur everywhere in some sense where you have logics. Temporal logics, other things as well. But now that I hope I at least gave you an idea of how widespread these calculi are, now we have to really go to the calculi that are also have really good computational properties. And we are not yet there. So the G1 systems are good, but it's not yet the full picture. So, oh, this is still some general remarks about what I was saying it in a bit different format, but it's maybe good to also mention indeed what I've written here. So it's true that if you look at foundational systems such as set theory or type theory, then the details of proofs are often not so important because the systems are anyway very strong. You can do a lot, so to say. But if you look at the logics that I've been mentioning, like these modal logics, which have applications in computer science, you often want something feasible, something that you can really handle well. And so the proof systems that you want to study, you have some requirements there. You don't, hey, you requirement that the proofs are not unnecessarily long or other things. And now the thing is that what we will see is that the G1 systems were somehow still very faithful to normal reasoning. But what we're going to step to is what we call the G3 systems. And what you could say of these systems is that they have very good computational properties. So they're useful for proof systems, but also other computational things that we will see. So that's the plan. I want to apologize about the names of the systems, G1 and G3. But in the book by Troelstra and Zwichtenberg, Basic Proof Theory, that was for the first time that carefully all these systems were, so to say, put together. There's also a G2 system, but I'm not going to talk about that. But, and I want to, so to say, nowadays everybody uses this name. So I use them as well, but I realize, many people realize that they're not the most fanciful names, or maybe even a bit difficult to remember which is G1 and which is G3. But that's how it is. And what I already hinted on before was that we will see, in fact, how important the structural rules are. Remember what I said about G1, that the structural rules there, in fact, blocked a good proof search. Yeah, so we'll see. But of course, we cannot just take them out, because then maybe we can't prove enough. So we have to do something there. And that's what we're going to do. But first, this, yeah, I think it is a bit of a summary of what I have already said. So let me do it. Yeah, no, the rest is important. Yeah. So I said, I think this line already, that the G1 systems somehow still feel rather natural, maybe not yet for you, but if you really work with it, you will easily see like that to generate proofs, that goes well. But bottom-up proof search, for example, not. And there's one structural rule that we haven't yet mentioned, and that's maybe the most important of all, and that I will tell you about now. So this key structural rule is called the cut rule, and the formula phi, you see it on the slide, and the formula phi is called the cut formula, and you probably see why the word cut, the name cut here is given, because you cut out the phi. Yeah, so if you have premise gamma implies phi delta, and you have a premise that gamma and phi implies arrow delta, then you have, of course, gamma arrow delta. That's certainly a valid rule. And you have to think about it in terms of lemmas. So what you, in mathematics, you often prove a statement that, for example, psi1 implies psi2. You prove it in the following way. You say, well, there's a lemma phi, and I'm going to show that psi1 implies that lemma, and the lemma implies psi2. So then I've proven psi1 implies psi2. And that is precisely an application of cut, as I wrote it down on the slide there. Yeah. And this you often see in proofs to make proofs more structured or more conceptual to understand. So this is a very, yeah, maybe a bit quick way of saying, look, for if you want to make natural proofs, this structural rule, this cut rule, is very good to have in your system. Yeah, it's a nice and natural rule. Because without this cut rule, yeah, you maybe have to unravel the whole lemma to make a proof of psi1 implies psi2, in which you don't use this cut formula. So this is therefore a very important structural rule. And if you then look at the system that we have seen, G1CP, I'm going to talk for simplicity again at the moment about CPC at the moment. So if you do see G1CP has structural rules, and if you also add the cut rule to it, yeah, then it has 5 structural rules. And that admit using lemmas in proofs, and that is more or less saying that you can have very natural proofs in that system. Yeah, natural in the sense of mimicking real proofs. What you now have to understand is that G1 and G1 plus cut, they prove the same theorems. I haven't shown this yet, but I'm telling you, yeah. But that's not the thing, the issue here. But the issue here is that they do it in different ways. That if you have G1 and the cut rule, you allow way more proofs as proofs. So the area of proofs is this. Now the collection of proofs is much larger. Yeah, so that's the difference here. Now, nice as that may be, now we want to go to the proof system that's computationally better, and we want to throw out all the structural rules, yeah, cut and the others. And the beauty is that we can do that. And the thing is that we then have only to change one, or yeah, well, you could say 2 things in the system. So the G3CP, I'm now going to just say G3 for the moment, yeah. So G3 is the system C1 that we have seen, except for the structural rules, the weakening and contraction, they're out. And the actions are replaced by the following. You could call that the weakened forms of the action. So originally we had P arrow P as an action, and now we weaken it. We say gamma and P arrow P or delta, which is obviously valid. Also, it's a more general version. Yeah, so weakened, I meant in applying the weakening rule, because it's of course not a weaker action, it's in fact strong, yeah? And the same, as you can see on the right side, we do with the bottom action. We also add there the gamma left and the delta right. So if we do that and we leave out the structural rules of G1, we obtain a system that is in fact equivalent to G1 plus the cut rule. Yeah. So this implies that G3 is sound and complete with respect to CPC, just like G1 is and just like G1 plus cut is. Wait, let me, oh no, let me, yeah, I want to pause a moment to say something about the cut elimination theorem. I'm not going to prove it because it's a long proof. It's an inductive proof on the depth of derivations. And you could say that it's one of the hallmarks of structural proof theory. So what is interesting is that in many, many cases where people want to obtain such a nice G3-like system, say for a certain modal logic K, yeah, they use also this cut elimination method that here was first developed by Gensen. And it has a lot of details, but in many cases it's still very close to this original proof. So it's a very useful and successful technique, so to say, that Gensen here developed in the proof. So it's not an easy thing, it's a hard thing to do. Now I'm not going to prove it also this, but remember my discussion on G1, on the rules of G1, and where proof search would be difficult, and that was in the structural rules. So maybe you therefore believe me if I say that now with G3, you have, this is very good computationally. You can really start with a sequent, apply the rules backwards, yeah, and look for proofs. And that is then terminating the meaning that process will end, and you can decide whether you have a sequence that's provable or not. So it gives you also decidability of CPC. Of course, we know that, but to show the usefulness of the system. So we have here now a system without the structural rules. And now I'm also summarizing again why we are happy to get rid of these rules. So for some applications, these rules are a burden, namely for proof search, as I said. Derivations don't have the subformula property. You could better say what is good about G3 is that it has, and what the subformula property means, if you prove a sequence, then in the whole proof, there only occur formulas that are subformulas of the end sequence. Yeah, that's also a very beautiful property. Yeah, I said it here all in the negative, but I'm thinking about it in the positive. So I'm saying a proof of the decidability of the logics is not straightforward if you have a G1 plus cut system. And for the G3 it is, for the reasons that I briefly sketched about the bottom-up proof search makes it possible to have a decidability algorithm. And there are a lot of other properties of logics, like for IPC, also has a G3 system, so without structural rules, and then you can prove the disjunction properties, more or less a trivial observation, while not in the G1 system. Oh, sorry, stupid. I wanted to show them while I was talking about the structural rules. I'm sorry. I'm a bit late. Yeah. Okay. And so we have the G3 systems. Now, yes, let me think one moment. Yes. So the remaining part of this chapter, I want to describe how this process that led me from G1 plus cut to G3, how also that is something you can do for many logics. So I had this slide for modal logics claiming, okay, all these G1 systems we can make for all kind of logics. But I wanted to say that also this step to G3 is very universal. You see everywhere in proof systems, in proof theory. But before I do that, I wanted to say one thing that is to stress again the difference between G1 and G3, namely that if you think about proof systems, then of course often it's also important to know whether the proofs in a proof system are simple or not simple, or long, even if you count precisely and you see the proof is a tree and you say the length of the proof is the length of the longest branch, then of course you can be interested in saying, okay, I have here this proof system. How long are the proofs in this system? Maybe compare to another proof system. So here G1 and G3, what's the relation there? Is it similar or very different? So you have a calculus here on the slide, G, arbitrary now, with a cut rule. Think of a G1 system, and it has cut elimination, maybe, so think of, you can prove that it's equivalent to a G3 system without cut. You can ask how much does it cost? And what I mean with that is what I said in terms of the length of your proofs, yeah? So if you have a proof that contains in G plus cut that contains cuts, and you remove all the cuts by the cut elimination method, then the question is how large or how small, or what happens with the proof that you end up with? How does it relate to the proof, the original proof? And then I have a theorem that was already proven by Gensen, who observed that if you have a derivation in G3 plus the cut rule, so I threw it in, and suppose that the cuts, you have cuts, so cuts in the proof and in the derivation D, and suppose that size of the largest cut formula is n, then the theorem says there exists a derivation d prime of the same sequent, but then in G3, so without cuts, such that the length of the longest branch, that is between the bars, so the length of d prime is smaller or equal, to the expression on the right, and that's a tower, you see it below in gray, it's a tower of 2's of height n, and the last power is the length of d, Okay, first let me say this is a constructive proof by Gensen, so he really does the cut elimination theorem, and he observes how the proof changes all the time, how it grows, in fact. And it can grow a lot, as you see, because this number at the right is, of course, much larger than the length of D itself. This, so to say, was strengthened, this result, by showing that the bound is actually sharp. And I think that was in the 70s, shown by Orevkov and Stedman independently. So the bound is sharp, and what we mean with that is that there are indeed sequences, say SM, that have linear proofs when you allow cuts in G3, but if you remove them, their size is at least 2 with the index m, that is this power of height m. So you see, okay, G3, good computational properties, but it makes proofs a lot longer in some cases, So that's again a nice thing about G1. So I just wanted to mention that to you because it's a very famous result, and I hope that it gives you more feeling for these systems. So in normal words, removing cuts is costly. Okay. holds for many other systems, G3I, etc. Has a similar, not the same, the bound is even a bit larger, but similar results hold. Okay, here we are. Okay, summarizing this chapter, what we have seen it for classical logic, but I'm saying it is for many logics. You have a G1 system, G1L for your logic L. You have a G3 system that has no structural rules. You prove that they are equivalent. That is not trivial. The cut elimination theorems, often hard. Then I, so to say, hope I have convinced you at least a little bit that the G1 system with cut is good for relatively faithful capturing proofs, mathematical proofs. The G3 system, sorry, the G3 system has good computational properties, such as the subformula property. So in every formula, if in a derivation, it's a subformula of the end sequent. So you even could call them pure, so saying something like that in a proof, you're not using anything that's not already, in some sense, in the end sequent. Yeah. So that's about sequent calculi and how they are used. And we have seen some examples that I now put in the example, and there are many more. Okay. Would be a nice time for a break, but we don't have a break, we continue. Here the last line is maybe good to mention, yeah, that often once people have found good calculi, then often the proof of cut elimination can be hard, but still straightforward in the sense that the method is known. But the intriguing thing is coming up with good calculi. So I just wanted to stress that. That's a very nice, yeah, sometimes very creative way. Yeah, and it's also amazing that I don't know, Gensen came up with these systems so early in proof theory with such useful systems. Okay, we arrive at the last chapter. All these sequence calculi. So I have described sequent calculi, and I have said many times how useful some of them are. And here I have some more properties where you can use your sequent calculus to prove these properties of decidability, of interpolation, Herbrand's theorem, all kinds of things where these G3 systems are very useful, sometimes have even more elegant proofs as a semantical proof, but that's maybe me speaking as a proof theorist, yeah? So might be different for you. But knowing all that now after the 2 chapters, then of course a very natural question comes up. If you have given your favorite logic, does it have a sequent calculus? Yeah? Well, that it has one is of course certainly true. You take, for example, if it's classical calculus, you take G1 and the cut rule, and you add the axioms arrow phi for all the theorems of your logic, and there you have your calculus. Yeah. But of course, that's not a calculus with good computational properties. So it's not a G3 calculus, for example, without structural rules. So there is a real question there, but we have to make it a bit more precise, namely, has a given logic a good sequent calculus? Now, of course, if we were all together in a room, I would ask you to give some hints what you would think would make a calculus good, but I'm not going to do that. So I just continue first by an obvious sentence, namely that good, of course, depends on the applications. We saw it already. I said G1 is good for some things, G3 is good for other things. But what I want to say now, I'm totally in the realm now of G3. I want good computational properties in general. Yeah, of course, I'm not going to solve this whole problem in that sense, but this is the area, the kind of calculi that I'm after now. Yeah. So it depends on the applications, but I'm going to name applications that will be useful indeed in our setting. Yeah. So good in terms of the G3 style, the computational style, you could say. Structural rules are admissible. So it's like you want them to be, to be admissible, but not in the system, because then they block good properties. So cut free, so you don't want the cut rule in the system. You want things like the subformula property. You like G to be finite. Well, that's often the case. And that proof search is terminating or semi-terminating. I'm not defining the notion, but kind of a weaker form. In some order on the sequence. Yeah, we'll get to that in a moment. So these are all kind of notions that you could think of. Now, for concreteness sake, this talk I will be talking about sequent calculi G that I call good if they have 3 properties. If they are terminating, they are an extension of G3 CP in the classical case and G3 IP in the intuitionistic case by semi-analytic rules and focused axioms. I'm going to define all these notions, and between brackets, single conclusion in the case I'm considering G3 IP, so in the intuitionistic case, but I'm now first going to talk about the classical case. So this is what I chose, and I chose this also because these are in fact now the properties that we really have good methods for, so that really, well, we have results, but it's definitely not the only notions of good that I'm thinking about, so to say. You can do this, also for other notions, or at least we hope. We're working on that. Terminating, yes, I want to tell you what I mean with that. I mean with that the calculus is finite number of axioms and rules. It's also instance finite, by which I mean that for every sequence, it may be the conclusion of at the most finitely many rules. That is that I want. And there's a well order on sequence such that every proper subsequent comes before the sequence. So I have a sequence, and if I take out some formulas, then I have a proper subsequent, and that should come before in the order of the original sequence. So literally it becomes smaller than also in the order. And in all rules, the premises come before the conclusion in that order. And I'm not going to show you the rules again, but hopefully you vaguely remember that indeed G3 is terminating. That we have, for example, I mentioned that about the premises coming before the conclusion. And also in the intuitionistic case, G3I, we have that property. So they are terminating. Many other logics are, for example, the modal logics that I've just shown you the definition of, nothing else, but they are terminating. And we have also systems that I'm not going to discuss, the G4I systems for intuitionistic modal logics, but they're also terminating, just to show you that they occur very often. Good calculi, so the other 2 definitions are still to come, but these good calculi, they are very useful in investigating logics. They are really an excellent proof theoretic tool. So we're getting closer to a precise question: which logic do or do not have good sequent calculi? Now with the real definition. I wanted to mention here, but only briefly because of lack of time, there is other work on the existence of sequent calculi. And the interesting thing is that these are used very different methods. So there is work on the existence of cut-free proof systems, and especially with or without additional structural rules. And in the work that I mentioned there by Bellardinelli et al., they used algebraic methods. So it's very different what we're going to see now in this chapter. And a similar thing that Sarah Negri is also working on existence questions, but she uses labeled sequent calculi, which is also quite different in how you investigate. Okay. The question. So the positive part, yeah, is that a logic has a certain sequent calculus. And there are, well, I stressed that many times, there are many of these logics around, there are many of these results. You have given logic, someone builds a proof system and it works, very nice. And sometimes someone comes with another sequent calculus, also nice, yeah? But there are not many negative results saying, well, oh, sorry, yeah, I was a bit ahead of myself, yeah. Proving that a logic doesn't have a certain calculus. And let me first show you the next slide because I mixed it up a bit. This is still about the positive ones. And maybe if you look briefly at it, I think we can skip it because he said it already. I said that there are so many results where you have the positive result, a logic has a sequent calculus. Yes, this is the slide I want to continue with. So now really the focus on the not. And the thing is, of course, that if you have a logic, you cannot, there may be, I don't know how many sequent calculi there are, and you cannot, of course, one by one, I'm going to show, okay, no, this calculus doesn't work, this calculus doesn't work. You cannot do that. So you have to think of another way, but then the question is, how exactly? Well, yeah, what can I do? And the thing is that in universal proof theory, we have a method that's in some sense, I would say, strikingly simple, but applying it well is surprisingly difficult. We'll see both facts, we'll see. So the method is in some sense similar. It's the following observation. So suppose you have a class of logics like modal logics or intermediate logic. And there's a subclass, so a subset of the, let me speak for concreteness now about modal logic. So there's a subset of modal logic, C prime, and a property that we can show the following. Any logic in C, so any modal logic with a good calculus, we have the definition, has property P. Suppose that you can show that. And the second one, you can also show that in this smaller class C prime, no modal logic in that class has property P. And then, very easy contraposition says, oh, but then it is so that the logic in C prime, that is in C prime, it cannot have a good calculus. And that is the negative result that we were after. Of course, the success of this really depends on how large the class C prime is and also how rare P is. Yeah? Because what you want, of course, we want negative results. So results of the form 3, no logic in C has a good calculus. Wait, sorry. Yeah, exactly. Yeah. Yes, because if C, sorry, I confused myself. If C prime is namely large, then you have a lot of modal logics for which you have shown that they cannot have good sequent calculi. So that's your negative results. And what I will do on the next slide is I will discuss this method in a little bit more detail for the class of intermediate logics. I just chose a class, could have been also modal logics, but I very much like this class myself, yeah? If you don't know them, as I said, just think of a class of non-classical logics. So I will be a little bit more, I'll get to provide a little bit more details although for real proofs, I'm afraid there's no time, but I can say a little more. That was, again, the definition on the slide of good. And now I'm going to tell you the other parts of the definition, terminating result, but now focused axioms and semi-analytic rules. For now, focused axioms are just, I didn't write that here, but they're also the normal actions of G3 and also actions of this form. So to say, simple actions. More interesting are the semi-analytic rules. Because what you here have, did I write it? No, yeah, it is also, let me say this, it is a bit simpler than in the literature, just for obvious reasons that I wanted to fit on the slide. So this reads very long, but how you have to read this, I didn't give you all the details on the slide. I will say that in Word. Oh, wait a moment. Say that in words. So what you have to look at is the following, that the gammas and the pi's, they are all multisets, symbols for meta multisets, and phi in the conclusions, that's the only real formula. So these are, so to say, rules where you introduce one formula and the rest is mating multisets. And in the top you have all formulas and something that's not on the slide, but that all variables that occur in the premises occur somewhere in the conclusion. Yeah, so I still wrote it with a lot of generality because I wanted to show you that it's not a very restrictive requirement, that many rules are semi-analytic. Yeah. So for example, the right rule, and I think we don't have time to really show that this is an instance. It's maybe more interesting to see why the cut rule is not semi-analytic, namely because you have this cut formula phi, and it can contain variables that occur not in the conclusion. So then it's no longer semi-analytic. Yeah? So many rules are such. For example, in G3, namely, you also have my one formula in the conclusion, and the rest is all multisets. So that shows that it for G3 also is all semi-analytic. Okay. So now we have the whole definition of good. Yeah, it was this termination and then this requirement on the rules. I have again here the method, nothing changed except that I'm now really talking about intermediate logics. Let me see how much time I have. 20 minutes. Okay, now that I can do something here. Yeah. So now the last piece of the puzzle is the property P. And as I said, the P should be rare because our conclusion want to be that there are many intermediate logics that do not have a certain calculus. That is the results that we want to prove now. Yeah. And I'm explaining it for uniform interpolation, which at the moment is still also the most successful, the property for which we have the most results, so the most successful one. But also here we're considering other properties. Okay, now I have 1.5 slides with definitions of interpolation. Interpolation is probably you all know, just so I have it here on the bottom of the slide, but I'm going to uniform interpolation, which is quite technical, so I'll take some time, but maybe have a moment to look at the bottom of the slide to recall what interpolation is. If you improve a formula, an implication, phi implies psi, then there is an interpolant, a formula that phi implies, and that implies psi, and that can only contain the propositional variables that occur in both phi and psi. Yeah, that's the, okay. Interpolation is nice, but we're going to use, and I will explain why later, uniform interpolation. So as the word already says, it's a strengthening of interpolation, a pretty severe strengthening, so to say. Yeah. Also in complexity, it's not an easy notion to, yeah. So, and you have equivalence in algebraic terms as well, but here I really stay proof theoretic because it is a proof, talking proof theory. So in the first sentence one always says when one introduces uniform interpolation is that it is an interpolant that also that depends only on the premise or the conclusion of the implication. We saw the implication phi implies psi. And in fact, you're not then looking in uniform interpolation for the phi implies psi, but just for the phi in some sense. Yeah. And here is then the more formal definition is that you say, for any formula phi and any propositional variable, yeah, there are two formulas, the existence P and the for all P, and they are called uniform interpolants, the existential one and the universal one. And they have the following properties, namely that for all psi, so here you see it is an interpolation, but then for all psi, so to say, yeah. So for all the implications, psi implies phi. No, maybe let's first do the right one because that reads easier. So there you really have, so it has to be a uniform interpolant for phi. So that means that whenever phi implies psi and P is not in psi, then this interpolant already implies psi, the existential interpolant. Yeah. And on the left is the same, but then for the universal quantifier, you could even, if you find the notation strange, you could think of for example, if you look at the existential one, that would also hold in predicate logic, so to say, for the existential quantifier. Yeah. They may maybe help you remember them. So one of the things, yeah, also as in predicate logic, phi implies there exists a p phi, and for all phi implies phi. And here is, for example, p implies q and not q. What you have, to put it again in another way to make you familiar with this, you could also think that the existential interpolant axiomatizes all the p-free conclusions of phi. Yeah. So if you here have there exists an q, there exists a q and then this formula, then you have to axiomatize all the q-free consequences of this formula, and that is indeed not p. Yeah. But it's all way less trivial here than in the interpolation case. So yeah. And I'm afraid I was in doubt whether to show you also this at the end of the lecture, but I thought I do for precision's sake. What you see here in this definition is that I also want to have the notion of sequent interpolation because I'm going to prove and use uniform interpolation for sequence. So I therefore had to define this, and maybe if you look at it, I hope there's a lot of things familiar. So the pi and the sigma, yeah, is you have to think on as the psi here, and the S is the formula phi, and maybe just to not take too much time here, if you look, for example, at the first displayed sequent here, you see the gamma arrow, there exists the p as delta, yeah? That is kind of a generalization of the example where we have phi implies there exists a p phi, yeah? Maybe because it's at the end of the talk, let's just say there is also this sequent notion, yeah? And it relates, as in the lemma at the bottom, that's exactly as you would expect. The calculus for the logic has sequent interpolation, uniform sequent interpolation, then the logic has uniform interpolation, yeah? If you're tired, just believe me that we can do. Now I want to show you, these are really the last slides, results about uniform interpolation that are relevant also for this talk. Let me first start with the PITS result that IPC has uniform interpolation. I always mention this because the proofs, I started to develop this project and this method based on the proof, the syntactic proof by PITS that is very beautiful. So I always like to mention it. And it was also the first result on uniform interpolation. There followed a lot of results for uniform interpolation that I just wanted to show you. You see here GL, K, KT. They have uniform interpolation, but interestingly, there are also very natural logics, S4 and K4, that have interpolation, but they don't have uniform interpolation. This is also kind of an intriguing property on what does it mean. This is my favorite result. You'll see why later in the next slide. Therefore, the book by Maximova, that's on the slide. It's not in that book, it's way earlier, but together with later results by Kalardi and Savadovsky, Maximova proved that there are exactly 7 intermediate logics. They have all interpolation and all uniform interpolation, and that's it. No other intermediate logic has interpolation or uniform interpolation. And Maximova had similar results at the bottom of the slide here, that also among extensions of S4, she has very interesting numbers, at least 31 and at most 49 logics with interpolation. Yeah? And she has more results of that kind, and they will be important for us. Now, the thing is that you can show that, I gave you the method, but now I'm going to give you, immediately I'm going to the results. So that will the whole last part of the talk will just be some of the results where we could apply this method and where we could use some of these already known existing results from the literature. Yeah, you will see how. So what could be shown, this was one of the first results in the 2019. You can show that if an intermediate logic has a good calculus, then it has uniform interpolation. And I'm not going to give the proof, but it's really proof theoretic. So you really define the uniform interpolant on the basis of the rules of the calculus. And then you show in some sense that for all the rules, if the premises have uniform interpolation, then so does the conclusion. So, and then you have your inductive argument. So that was the result. Or later than I said, it's earlier than I said, 2017 indeed, that any intermediate logic with a good calculus has uniform interpolation. Just for those of you who know, there's a line in gray that I'm not even going to read, but if you know G4, you might find it an interesting line. Now let's compare this result to this result that I was discussing, that there's exactly 7 intermediate logics with interpolation. Then we have as a corollary, simple corollary, no intermediate logic except those 7 have a good calculus. And that was exactly the negative result we were looking for. We have now the whole class of intermediate logics, and only 7 have a good calculus. So all the others have not. And knowing that this notion of good calculus was large, I mean, these are infinitely many proof systems for which we now suddenly know cannot be a proof system for these logics. We have also positive corollaries of what we've done, but these are corollaries like that CPC has uniform interpolation. They are well known, but I just wanted to show that the method also can lead to positive corollaries. I'm sorry. I'm sorry, I'm recovering from the flu. Wait a moment. Sorry, sorry for that. Now, Amir Tabatabai and Rahele Jalali have generalized these results to substructural logic, sorry. So they have shown also there a similar result that I'm not going to talk about, because then I would have to also introduce the substructural logics, etc. So this is more, these slides are more to give you kind of an expression how widely the method has been applied. And therefore also this slide is about modal logics, classical and intuitionistic. So also there we have a result just like as for the intermediate logics. And just as I did on the previous slide, I combined it with results by Maximova of the 80s and 90s, 1980s, 1990s, that I just discussed you. I said this result about the normal extensions of S4 that are at most 49 with interpolation. And then again, these two theorems together give a nice corollary, namely that none of these extensions, as they are in Maximova's result, can have a good calculus. So again, a strong negative result. For K4 and S4, we know that they don't have uniform interpolation. I mentioned that, the result. So goals also here they have no good calculi. And that's kind of increasing because they have nice calculi, but not good in the precise sense. This termination is a problem, something I'm very much intrigued by at the moment, but I don't have other results for you to tell you than this one at the moment. And just to give you an expression, as what I said earlier, is that we have this method because we wanted to have a method to prove negative results. So that's our final aim. That's what we do. So we're not so much aiming to prove uniform interpolation. We are aiming to prove this negative results for which we use uniform interpolation. But it might be nice also to know that our methods are also really allow to prove theorems that are known in the literature, but nevertheless, and sometimes you prove new theorems. So as in 2019, that the intuitionistic modal logics IK and IKD have uniform interpolation. All right. Going towards the end, let's, this is just a slide to tell you what we're working on at the moment. And with we, I mean myself and Rahele Jalali and Amir Tabatabai, who are also very active in this area. Sometimes we want the class of good calculi is still too restrictive or too large, and then we want to change these notions a bit. It's something we're working on. What we're also working on is replacing the property of uniform interpolation by something else, like the disjunction property or other rules. This is something that Jalali and Tabatabai recently wrote a very beautiful paper about that has been submitted now, is under submission. I am also thinking about tightening the connection between terminating sequent calculi and uniform interpolation, because in some sense this termination seems to play a very important role in the proofs of uniform interpolation. But how exactly it is needed, in general, or maybe let me say, in how far having uniform interpolation says something about having a good proof system, I don't know. I really don't know, but I'm working on that. This is the last slide, at least the last slide with content. I show you in full and go over it quickly. The original question is at the top: which logic do have a good proof system and which do not, in fact? Now, I've shown you in this talk many classes of calculi for which we can do something. I showed the proof system, sequent calculi. I told you what good was. And I showed this theorem that having a good sequent calculus implies uniform interpolation. And on the basis of that, I showed that many logics do not have good calculi. And as a byproduct, I said, well, we have this notion, way to prove uniform interpolation. And we were even able to prove some new uniform interpolation results in the area of conditional and non-normal logics. The related questions I already briefly mentioned on the previous slide. So could we change the notion of good and see what happens? And another thing that I find very interesting is to think about how it, for example, applies to really different logics like predicate logics, because that I don't really know yet. And I think this is a good moment to stop. I thank you, and I hope you learned something about proof theory and about this particular area in proof theory. Okay, that's it.
Okay, let's first thank speaker Professor Rosalie Iemhoff for this very wonderful lecture. Our students learn a lot from the lecture. We have around 15 minutes for the question and the comment section. Okay, first of all, let's welcome the interlocutor, Lin Zhe, and for comment or question, please.
Wait, maybe may I interrupt? Sorry, shall I stop sharing my, or not? Or do you like to have the slides still as the main?
Maybe I can I have your slide, because I will mention some points in your slide.
Very good. I'll keep them there. Yeah.
Yes, thank you. So, thank you very much for your talk. It is very interesting, especially and really interesting on the way to prove that a general way of proving the UIP. Sorry, I say UIP is more easy.
Yeah.
The UIP, and then using these measures to create a condition to say what kind of logic has a good calculus or not good calculus. But I have some questions on this. Is there the good calculus has any restriction? I mean, that is it restricted to only the G4 extension, or I may have more free condition to any calculus? I mean, because all the sequent calculus you present your slide is, I can say, in more Gaussian style sequent calculus, right? So if I wondering if I replace some kind of label sequent calculus display, or even nested sequence or something else, then is there the result preserved or something may change?
Yeah, I think that is a very good first question immediately, because in principle, that can certainly be done. I mean, the method is so general that especially for labeled calculi, I think one can do it. But what is different is that often for these proof systems, like deep inference or label, these properties that I use, like interpolation or uniform interpolation, they are not so easy to prove in these systems. For example, if you have labels, but that doesn't mean that there maybe is a property closely related for which you can carry out the same method. So my answer would be, in principle, yes, but it's not that I already immediately see, all right, you can do just like for G3. That I don't know yet. Yeah. Yeah.
Okay. Yeah. So I continue my question is that because like in these measures, when we used to prove the UIP, that this property is somewhat not very related to the system described. It is more like a semantic condition for the logic.
Yeah.
Yeah. So if in your last slide, you mentioned that can we describe some other property, right? To use these measures. So if I change this property UIP into a more pro-theory property like type elimination, then there is a quick problem that I think there may come some problem because then it will depend on the calculus you are talking about.
Maybe I'm not understanding.
I mean
Could you
that,
say, I don't, so
yeah.
what you mean systems?
I mean,
Maybe
so,
try it again in a different
yeah,
way.
yeah. So I say that if I replacing the UIP property and to make some like type elimination or something other like subformula property or maybe some more strictly subformula property, something like this as a property, and then I consider good calculus. Then I think maybe at this time, then the good calculus may have to restrict it to talking some kind of calculus. Because the reason is that when we discussing the type elimination in display calculus, it will really different from the, you can prove the type elimination is simple,
Yeah.
and also you can prove the type, but the type elimination is not exactly like you prove in the LK. In fact, you have the type elimination, but the subformula property slightly change, in fact, because you hidden something in this proof. So I
Yeah.
mean, if we consider a proof theoretical property as a property we deserve, then the problem is that whether when I consider the good calculus, then this calculus maybe I should restrict it to some range or
Yeah.
or
I think yeah.
universe. Yeah.
Yeah, so I think I'm getting it now. So you're saying in some sense, if for example you go to display calculi,
Yeah.
the notion of good is too restrictive.
Yeah. Something like this.
I see what you mean. Yeah. But okay, I didn't realize that. Yeah, so it so I see all.
Because one thing is that usually a display calculus is difficult to have termini.
Yeah.
So it depends. I mean, maybe sometimes it depends on the form of the calculus we discuss.
Yeah. But are you saying that in the display calculus, I'm not so familiar with it, so but you have a cut-free system in the end, or
I mean, in the display calculus, when we have a display calculus, prove the cut elimination, but that's different than we prove the cut elimination like in G3CP, because in G3CP, we prove cut elimination, we get immediately have a very strict subformula property, and then we also have the terminate, and we have very good property. But in display calculus, if we prove the cut elimination, sometimes like a fake thing, because you have a subformula property, but in fact you can still change. You can display left to right, right to left, and then in fact you couldn't have any restriction on the tree of your proof, and you even cannot have terminate. So
okay, I see. Yeah.
In such a case, maybe if I want to discuss the property, which is more in pro-theory version or pro-theory property, then maybe the good calculus maybe should we restrict it to some area? I mean, should exclude it like play or some kind of special, very strange or special kind of form of
yeah. I think this is maybe the dull answer, but I think you're right that it's for in some sense with every class of logics or calculus. You have to think again what you think are the good proof systems, or that I fully agree with. Yeah. Okay. Yeah.
Then I have one more question is about this proving this proof. There is I wonder if is there any if this measure can show us some way to. So I mean, we're talking about what logic has no such property. Even because as I know that many kind of this proof is done by semantic, not syntax.
Yeah.
So is it a way to show that an idea to prove like maybe can be extended to show that a logic does not have UIP in proof theory way?
Yeah. That's a good point. That's a good point. I make use very much of the algebraic proofs about uniform interpolation, and but that's how do you say? Wait a moment. I have to. Yeah, I mean, in some sense, I don't expect a proof, theoretic proof, at least it's not what I'm working on, because I'm, how do you say? Yeah, maybe maybe I should say that at the moment, I have no idea how one would prove that proof theoretically. Maybe I should say that. So I really rely on the semantical count, because these are counter examples always, showing that something is not, So I have no idea. And so, for example, for the area of intuitionistic modal logic, where we have a lot of results, but the thing is that there are not much results known at the moment about negative results about intuitionistic modal logics, only for so it is kind of an issue in some sense that you are addressing here. And but it's not that I'm trying to prove myself that something doesn't have uniform interpolation. I'm just talking to algebraic logicians and I'm telling them that they should prove.
I got it. I got it. Yeah.
But it's a good point you make, absolutely. Yeah.
Okay, thank you. And, okay, I have no other questions, so maybe I can play it back to the.
Thank you. Very nice. Yeah.
Okay. So you have finished your question, right?
Yeah, I finished my question. Yeah.
Oh, okay. Thank you. There's a question from our audience, from Vincent. So I can repeat his question. His question is that first time I see card elimination presented like that. So card cannot be eliminated without also eliminating all other structural ones, except for the exchange ones. Whatever one could like. I post a question in the chat box.
No, that is not quite true. You No, you can also have your proof system with structural rules and cut, and you just eliminate the applications of cut, but you keep the other rules. I hope I get your question right, but that you can do. Because you were saying first time I see cut elimination presented like that. Maybe because you often see it in the way so in LK by Gensen, that the cut rule is really in the system and then you eliminate it. Is that? I think it's clear. Okay.
Okay. Yeah, it says that in Gensen's original proof, he removed cut, but also remaining or other structure.
Yeah.
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 Okay, thanks for the question. Any other question or comment? Okay, if no, I have two small questions. One question also Ninja wants to ask about. What's your motivation to introduce the notion of good sequent calculus? So for different notion, maybe the picture is totally different. So this is the first question. The second question is, you show that any intermediate logic with good sequent calculus has UIP. How about the converse? You see that there are exactly 7 intermediate logic with UIP. Does all these 7 intermediate logic all has good sequent calculus?
Yeah, I start with the last question. I no, that's not the case. There are definitely, at least there are no calculi known. Not for all these logics, there are good calculi known. And this is in fact something I'm working on. In fact, I don't think that UIP is really implying a good calculus. That would be too strong. I can't imagine that. Also what the interlocutor said or so, you think of UIP also as a semantical notion, so why would that imply the existence of a calculus? That I don't see. But what I do work on is the notion that if you know already that the logic has some kind of calculus, and then also knowing UIP, that may maybe then say something about the calculus, but that's a very much weaker thing. I see the UIP really, as I said, as a tool. So, and it works well, but I don't think that there's a really deep connection between the calculi and the UIP. It's mere a good tool. Yeah. Yeah. And now, could you please remind me of the first question?
Yeah, first one is what's your motivation to define the notion of good sequent calculus in this way? For different notion of good sequent calculus, the picture may be different.
Yeah, sure. Yeah. No, yeah, that I can really answer. So the thing is, I studied PITS, UIP for intuitionistic logic. And when I read it, I saw two things. I thought, okay, this could be way closer to calculus disproof than it now is. And once I've wrote that down, I thought, hey, one can generalize that a lot. So then I suddenly stepped away for concrete sequent calculus. I just was looking what I needed in the proof for UIP. And all this generalization then led to the notion of a good calculus. That's how it worked. Yeah. Yeah.
Okay, thank you. Any other question, comment? Okay, if no, we have run over our time. Okay, let's thank again for the speaker with wonderful lectures. And also we thank Lin Zhe for the question and comments. Also, we thank our audience attending our lectures. Okay, lastly, we thank our organizer, School of Philosophy at Wuhan University. Okay, that's all for today's lecture. Okay, maybe it's time to say goodbye.